in the coupling line the other day in class related to this multiple constraint problem, the case study about the connecting rod. And so I just want to give it another shot here and spend a few minutes talking about it. So this is the plot that we're looking at. Notice that we have M2 on the y-axis, that's density over Young's modulus to the 1/2, and then M1 on the x-axis, density over the endurance limit, which we called sigma sub E. One of the things I want you to notice is that the modulus is given in units of megapascals, technically the square root of megapascals, but the main thing is we are taking the gigapascals and multiplying by 1,000 to get megapascals, and that's just to keep the units of the similar dimensions, which is helpful when we do some calculations. So we see these two coupling lines. One, F over L squared is equal to 5 megapascals, and the other one, F over L squared, is equal to 0.05 megapascals. Let's talk a little bit more about these and see where our materials lie on these lines. So here is, again, the two materials indices, M1 and M2. And then we had this coupling equation with F over L squared there. What I want to do first is just plug in values. We're going to use alpha is equal to 0.8, and then we're going to look at the two values of F over L squared and see what that means in terms of the relationship between M2 and M1. So first of all, for the 5 megapascal F over L squared value, M2 is going to be equal to 1.8 times M1. And for the 0.05 megapascal value, it means M2 is going to be equal to 0.18 of M1, a factor of 10 less, which makes sense because the two F over L squared values are different by 100, and then we have a square root there. So we're essentially taking the square root of a factor of 100. Now, I'm indicating the, the 5 megapascal F over L squared by this red dot, and the F over L squared of 0.05 megapascals for the black dot. And if we go back and look at our plot, and just fine, all I'm doing is going to the plot and looking at values. So when I have M2 over M1 is equal to 1.8, right, or M2 is equal to 1.8 times M1, here's 10 for M1. And again, we have megapascals in the denominator, so we can do this. And I go up here and find roughly, this is approximately 18 here, and that's where the line lies. Everywhere along this line, M2 is equal to 1.8 times M1. Let's do the same thing with this black dot. Again, now I have the same value on the y-axis, 18, but now on the x-axis I have 100, and so now I'm at 0.18. And anywhere along this line, you can go and find some other points, you're going to find that M2 is equal to 0.18 times M1. So they represent different regimes of loading on this material. Well, and let's just give you an example of what we're talking about. What's the difference between these two lines in terms of the loading? Well, let's just assume that the connecting rods are the same length, just to keep things simple, and I'm keeping it at 200 millimeters, which is what was used in the min-mass problem, just to be consistent. And what you see is that the force on the connecting rod for the F over L squared is 0.05 megapascals, is 2,000 newtons, and then for the 5 megapascals is 20,000 newtons. So what that's saying is that for the line associated with the 5 megapascal F over L squared value, the rod has to carry a much greater load for the same length. So we're just expecting a lot more out of this rod in terms of its properties, in terms of resistance to buckling and then resistance to fatigue, and at the same time we're trying to minimize mass. Now let's look at the materials and just calculate out their M1, M2 values, and then the ratio of M1 and M2, and then go back to the plot. So first let's look at titanium. Again, I have the density, the Young's modulus. Note that I'm using units of megapascals. This to be consistent, and because the value for the stress is also in megapascals. So M1 specifically for this titanium alloy, 6 aluminum, 4 vanadium. It's a fairly common titanium alloy, so it's not pure titanium. M1 is 8.3, M2 is 13, and we have a ratio about 1.6. So it's not exactly 1.8, but it's pretty close, and we'll see how that fits in. In fact, let's just take a look. So here we are again. Again, it's along this line, it's 1.8. The titanium 6 aluminum is 1.6. So, it's a little bit more in one of those two directions, right? So it's right around, and certainly this balloon with titanium alloys covers a very broad range. And so it's fairly close to that line. And again, we're going to go down this line and try and minimize the mass as best we can, get as close to the origin as we can, right? And for the higher loading situation, we're going to have to stick with titanium because that's as far as close as we're going to get. Beryllium wouldn't be a bad choice, but it doesn't lie right along the line, but it's not horribly far away considering. But for a higher loading, it's going to indicate that we want to look at titanium alloys. For aluminum, again, lower density, lower Young's modulus, much lower strength. Okay, notice that we have a factor of 2 Young's modulus difference, a factor of about 5 difference in the stress. So very different material properties in that sense. Still relatively stiff, but doesn't have the strength in terms of fatigue. So notice that my strength value is a lot lower. My density is lower too, but the strength value is about 5 times lower compared to titanium, more than that. But the density value is only a factor of, 1.5, something like that. And so you see a big increase in M1. M2 doesn't change that much, right? The modulus goes down, and so does the density, but similar amounts. And then we have this value of 0.36. Notice that it's close to the 0.18 regime that we were talking about. And again, if we go back and look at aluminum, this is where I have this dot is 0.18. All along this line, it's 0.18, right? And 0.36 is going to be more in this direction. But you see, I have a long way to go in aluminum alloys before I'm getting, values of where I'm going to leave the aluminum alloys. And so you can see kind of where this choice fits into the situation where we don't have quite as much of a load. Now, just for fun, or just a look, I decided to run the numbers for the nodular ion. That was in the min-max problem. We have an M1, actually very similar to aluminum. And what we see is the Young's modulus is larger by a fair amount, right? I don't know, about 2.5 times. So is the yield stress, right? And so the value of the density and the yield stress sort of changes, just cancel each other out, and you have a very similar value. But nodular ion has quite a bit higher of a Young's modulus, and we are taking the square root, so it's not as big of an impact, but it's still an impact. And its M2 over M1 is 0.6. And so if we look at that, first of all, cast iron's here, and I drew a dot here where this is about 0.6. So that we have 18 on the y-axis, and I believe roughly 12 on the x-axis. So it's going to give you a value of M2 over M1 of 0.6, more or less. Or I might have that inverted. Oh, no, it's right. Because that's 18, and this is not 12, it's 30. So that, or 20. So that, no, it's 30, I'm sorry. So this is 10, 20, and 30. So we have 18 over 30, which is about 0.6. And so that's our cast iron material. It's F squared over L. I'm sorry, that should be F over L squared, would be equal to 0.55 megapascal. So it's about roughly, if we're spanning 2 orders of magnitude from 0.05 to 5, we have 0.55 in between. But the thing is, okay, so this coupling line tells me about the loading conditions that I'm going to be expecting using when I'm using cast iron. And if I follow this line down, remember, as we get close to the origin, things get better. I pass through aluminum alloys, so that will give me the similar loading performance as cast iron, but much lower mass. And then I go through magnesium alloys, which will give me similar performance to cast iron, but a much lower mass. And then, of course, we end up with beryllium. So getting back to this, on the bottom, the aluminum is a better choice when you have lower forces. The titanium is going to be a better choice when the loading is larger. And finally, just to summarize, or just to say something about the cast iron is a low-cost solution for the moderate loading. It's a good low-cost solution, but we can lower the weight using either aluminum or magnesium alloys. Beryllium's the best, but the dust is a hazard, and it's expensive. Beryllium's over $100 a pound. Before you even take in the extra cost of machining it, because you have to be careful when you machine it. Aluminum's on the order of $1 to $2 a pound. And so just to summarize, so I hope you have a better sense of how these work, and you can just run the numbers. I suggest, when you're practicing this stuff, you just get out one of these plots and start reading numbers off of the log chart. And if you haven't done that for a while, like me, you can get over making your mistakes of this isn't 10, 11, 12, but 10, 20, and 30, right? And so just get used to that and get a little bit more comfortable with that. So anyway, I hope you found that helpful, and thanks for listening.